Hello everyone and welcome to lecture today. So today we'll be talking about how to go through and actually get a general solution to systems of linear first order differential equations. And it turns out by the end of the lecture we'll see that there's a very nice and I would say mathematically beautiful way of solving systems of first order ordinary differential equations. And what's so nice about it is that in many ways it is directly analogous and the same as how we went through and solved single first order differential equations. It just uses, we utilize some concepts from linear algebra based on the fact that when we're solving a system, we're solving a system of differential equations in n-dimensional space. But it's really remarkable that this formula, it's possible to go through and do this and write down an explicit form for the solution to a general system. For some motivation behind this, I want to recall something that you've probably seen or you saw a lot of in your original ordinary differential equations class. And this is a single linear nth order in general inhomogeneous ODE takes the following form. That's the nth derivative of the unknown function y with respect to t plus some function Pn minus 1 of t times the n minus first derivative of y with respect to t all the way down to P1 of t times y prime or dy dt plus some function p naught of t times y in general is equal to some function g of t. So this is what any general single linear nth order inhomogeneous differential equation will take the form as. And you'll hopefully recall that the solution method for such a differential equation involves looking at finding what's called the general homogeneous solution, the general solution to this differential equation where g is 0, and adding to it the particular solution, or a particular solution, to this differential equation. So today's lecture should hopefully clarify some of the reasons that this is a valid solution method, a valid solution procedure, and it's going to have a very similar way forward when we go through and try and solve systems, first order systems. And the reason behind this is relatively straightforward. This single ordinary differential equation can be rewritten as the following. And we're going to see that just like all of the other differential equations that are of order n that we've talked about, we can rewrite this as a system of first order differential equations. So I'll introduce xi1 as being equal to y, xi2 will be defined as xi1 prime, which is just y prime. Xi3 will define as xi2 prime, which in actuality is y double prime. All the way up to and including xi(n), which will be defined as xi(n minus 1 prime, which is just the n minus first derivative of y, where I'll just know this as yn minus 1. So we have then that xi prime is the vector xi1 prime, xi2 prime, all the way down to xin minus 1 prime and xin prime. Because xi is the vector xi1, the vector function xi1 to xin. And then this is equal to xi2, xi3, and so on and so forth, all the way down to xin. And then xin prime, or yn, can be solved for by just using this differential equations. This, when we plug in our xi notation here, the differential equation itself is the same thing as xin prime is equal to g of t, and then minus all of this stuff, which is p naught of t times xi1 minus p1 of t times xi2 minus each one of these terms in this sum all the way up to and including pn minus 1 of t times xin. So xin prime then, from the differential equation, will be negative p naught of t times xi1 minus p1 of t times xi2 minus every other term in the sum up to pn minus 1 of t times xin plus g of t. Which means then, if we rewrite this a little bit using what we know about matrix multiplication and matrix addition, this is the same thing as xi prime being equal to the matrix with zeros in the first column until we hit the function negative p naught of t. And we have a 1 in this column right here, followed by a 0, and zeros all the way down until we hit negative p1 of t, and a 0 and a 1, and then another 0. The zeros are going to go down the matrix like this, and or like this, and the last row of this matrix will contain all of the functions, negative p naught, negative p1, negative p2, and so on and so forth. Likewise, we'll have 1s all the way down until it's right here. Just to kind of give a reminder, this is going to be a 0. This term is going to be a 0. This term will be a 1. This will be negative pn minus 1 of t. Then the zeros go all the way up to here, all the way down to here. So it's this matrix multiplied by xi. There's xi1, xi2, all the way down to xin minus 1, xin, plus the vector of zeros everywhere except for the last component, which is g of t. This matrix is sometimes called the companion matrix to the nth order ODE above. So to this ODE right here, and this is sometimes called a forcing function. G of t is also sometimes called a forcing function as well, so don't get confused. But the main idea here is that this is, in general, our vector function of xi and t, which is, in general, a non-autonomous system of first-order differential equations. It's a linear system. Which is equivalent to the nth order ODE above. Which means that if we can solve this linear system, we can solve this nth order ODE, and the solutions between the two should kind of match up and give us some similarities. And sure enough, we're going to see a lot of different similarities. So in this lecture, we will investigate solutions to systems of ODEs of the form xi prime is equal to A of t xi plus B of t. Alright, so this companion matrix is specifically related to this single nth order ODE, but we've seen in general that we can have more general types of models, more general types of first order systems. So what we're going to do in this lecture is develop a variation of constants formula for systems of this form, which essentially will cover systems of this form right here, thus giving us a solution method that will give us the solution to any differential equation of this form, which is very, very cool. So a first order system of ODEs is linear if the function g, the right hand side of the ODE, where the ODE is xi prime equals g of xi comma t, if g is a function, specifically a linear function, or an affine function, of xi. The independent variable here is t, the dependent variable here is xi, and we know that for a linear ODE system, xi has to appear in a affine manner. So it can't, you can't have any nonlinear functions of xi, of any of the values of xi. So this means that g of xi t will be equal to some a of t times xi plus some vector b of t, where this is matrix multiplication. So a of t is a matrix of vector valued functions, or I should say it's a matrix of functions, and b of t is a vector of functions, so it's a vector valued function. And the differential equation will look like xi prime is equal to this matrix, a of t multiplied by xi plus b of t. We'll specifically say A is an n by n matrix of functions t, and B of t is an n by 1 vector of functions. And we'll assume throughout that these are continuous. For t in some interval from a to b, which we'll call I down below, just for brevity. So if we go through and list out the component form, so you do the matrix multiplication out and you list out what this is saying, this is the following. Well, if you do this matrix multiplication out, add this b of t, and you get that xi1 prime will be a11 of t, whatever that function is, times xi1 plus a12 of t times xi2 plus, and the sum all the way up to a1n of t times xn plus b1 of t xi2 prime will be a21 of t times xi1 plus a22 of t times xi2 all the way up to a2n of t times in plus b2 of t and this continues all the way down until we reach xn prime is equal to a(n)(1) of t times xi1 plus a(n)(2) of t times xi2 plus all the way up to a(n)(n) of t times in plus bn of t. So a solution to a linear linear system of first order ODEs is n functions that satisfy these n first order differential equations. So it's heavily dependent on the matrix A and the matrix B, and the coupling here is due to the matrix A. So these equations are all coupled together. The relationship between the solutions for each one of the variables is coupled through this matrix A. And I want to make the following notes, which give us a little bit more clarity on the notation here. If the matrix function A of t is a constant matrix, the ODE system, we'll call it star DE, is said to be a constant coefficient system. And using the results of the lecture today, in the next lecture video, we'll go over how to deal and solve for the exact solution of constant coefficient systems. But I want to present this general solution method today because it's more general. It applies to all first-order systems of ODEs. And the other notation here that I want to get down at the beginning is that if b of t is equal to 0, it's identically equal to 0, the system of differential equations is called homogeneous or homogeneous. So not homogeneous, homogeneous. And likewise, if b of t is non-zero, the system is called inhomogeneous. And this is going to be a very important distinction because it's actually going to determine how we go through and solve the most general solution for the IVP. We go through and solve for the initial value problem for any given differential equation system of this form. And the first big theorem we want to state is the general solution to the initial value problem xi prime is equal to a of t times I plus b of t with some initial value xi naught, where the initial condition t naught is in the interval I and xi naught is some constant. So the general solution to the IVP, this IVP right here, which a little bit later on, call this differential equation with the initial value star, exists and is unique on the interval I. And the proof of this actually comes from the previous theorem that we talked about, which is the theorem on the existence and uniqueness of solutions for the general nonlinear system of first-order differential equations, and it's entirely due to the continuity assumptions placed on a of t and b of t. And this is simply because if you take the partial derivative of g with respect to any of the variables xi, right, this will be a continuous function. And therefore, because our function g, which is the right-hand side of this ordered differential equation, is a continuous function, by our previous existence uniqueness theorem, this holds. So we deduce the theorem. So what I want to talk about and jump into is how to go through and directly construct the general solution to such a differential equation. And the end goal here is to get a very, very nice formula that's a variation of constants formula, but is sort of a generalized variation of constants formula. And we will see that it is a direct generalization in some sense of the formula in 1D. So the general method for solving the initial value problem from before is to split the solution process into two parts. And this will definitely be familiar to you if you recall how you solved nth order linear ODEs in your single ODEs class, your first introductory ODEs class. First, we solve for the solution that I'll call xi h of t, which is the most general form, the most general solution to the homogeneous form of star. So xi h is the most general solution to the differential equation system. Xi h prime is equal to a of t times xi h. Remember here, we're doing matrix multiplication, matrix vector multiplication. In general, this is, you want to make sure that you review your linear algebra as much as possible, because we're going to be using a decent amount of linear algebra in the foreseeable future. Once we've attained the most general solution to the homogeneous form of our differential equation star, we solve for a particular solution, xi p of t, where xi p is a particular solution of the differential equation star. So xi p is a particular solution of star. That just means that it's some solution which might not satisfy any of the specific initial conditions for the problem, but it does satisfy the differential equation. So the derivative of xi p is going to be the matrix A of t times xi p plus the vector function b of t. And with the homogeneous solution and the particular solution, then we can go through and express the general solution as the superposition of these two solutions. And this is just one of the many times that we're going to use what's called the superposition principle, which is essentially an inherent property to all linear ordinary differential equations. And this is one of the things that makes solving a general linear ordinary differential equation or ordinary differential equation system so nice. Nonlinear systems are much more complicated, and we don't have this nice solution method. But we will see, just like we saw for single linear ODEs, that sometimes we can make transformations for nonlinear ODEs to give us a linear system. Sometimes we can actually just use the linear theory directly on a nonlinear ODE by doing what's called linearization. So this is a technique that we'll talk about in a few lectures that's very useful. But you could ask, why is this a general solution, the most general solution to our ODE? Well, we'll answer this in the next couple pages. But just if you want to verify this, you can go through and do a direct verification that it will in fact solve the ODE relatively simply. And I want to justify in the next couple lectures why it's the most general. We call this the general solution to the initial value problem. But to go through and verify is relatively straightforward. We know that xi prime will be equal to the derivative of xi h plus xi p which will be equal to xi h prime plus xi p prime due to the linearity of the derivative, which will be equal to, well, xi h satisfies the most general solution to the homogeneous form of the equation. So xi h prime is a times xi h, and xi p prime is a particular solution to the inhomogeneous form of the differential equation. So this will be equal to a times xi p plus b of t. And I will actually, instead of writing a here, explicitly denote this as A of t in both cases because this variation of constants formula that we're going to get at the very end is, works in general. So using a little bit of linear algebra, the matrix multiplication is distributive, so we can rewrite this entire thing as A of t times xi h plus xi p plus b of t and because we define xi, the general solution to star, as this right here, we have that A of, this is A of t times xi plus b of t. Right, so this solution is clearly satisfying the differential equation, and we'll also see when we end up constructing xi h and xi p, we can directly construct these so that they also satisfy the initial value as well. So xi of t naught is equal to xi naught. So let's break this into two parts and discuss how to go through and solve for xi h and xi p. So in this part of the lecture, we will now discuss how to construct the general form, the general solution to the differential equation xi h prime is equal to A of t times xi h, which in the notes below I'm going to denote as star h for the homogeneous part of star. And right off the bat, we will need a couple of definitions that are essentially definitions that are coming from linear algebra. And this is the definition of what it means to have linearly dependent versus linearly independent vectors. And really, we need to extend this idea to vector-valued functions. So we say that k vector-valued functions phi1 of t, phi2 of t, all the way to phi k of t, defined on I, are defined to be linearly dependent which is sometimes denoted LD, and I will make use of that later on in the lecture, on the interval I, if there are constants C1 to CK that are not all zero, such that the linear combination C1 phi1 plus, and I'll be very specific here, C1 phi1 of t plus C2 phi2 of t all the way up to Cn phi n of t is equal to 0. Or the 0 vector for all t and I. So this means that if they're linearly dependent, it means that you can satisfy this equation right here by, say, solving for phi n in terms of a linear combination of all the other phis. Oh, and I just realized that this should be up to k here, and not Cn. And let's be very specific with our notation here. I'll underline these phis to denote that they're vector functions. Okay, so these are things that are in Rn. Same thing here. And if we have a concept of linear dependence, it also stands to reason that we would have a concept of linear independence. And this is a property that is going to be very important as well. So you could just define the linear independence as being not linear dependence, or the opposite of linear dependence. But in some sense, we want to be very specific here. We'll say that k vector valued functions are, so phi1 of t to phi k of t, defined on for the t in the interval I are defined to be linearly independent on the interval I if the only constants C1 to CK satisfying C1 Phi1 plus C2 Phi2 plus CK Pk, also all the way up to CK Pk, are 0. So the constant C1 equals C2 equals C3 equals CK equals 0 for all t in the interval I. So it turns out that these are two extremely useful ideas that are originating in linear algebra, but are going to be fundamental to defining the general solution to the homogeneous form of our ODE. And that's evidenced by the following theorem, which I won't be going over the proof of, but there's a very nice proof of in the book. And I will talk a little bit about how to go through and prove it as we go through and develop some of the theory that we're going to be using. So our first big theorem on solutions is the following. The homogeneous linear ODE system star H, so the homogeneous form of the ODE, has n linearly independent solutions on the interval I, and if Phi1 to Phi(n) are these n linearly independent solutions, the general or most general solution